I was having some breakfast, pulling milk out of the fridge, when the calendar caught my eye. Do you know what today is? Today is a day of reckoning, and I reckon we're going to hang our first motor on the MAHO milling machine. What you're looking at here is the apron, maybe the saddle. Heck, it might even be the knee. Anyway, that thing is the Z-axis bit of the MAHO milling machine. The part that goes up and down. Carries X-axis with it, the vise, the work, all that stuff. It's the part formerly known as the piece of junk taking up a ton of space on my workbench. And it's now back on the milling machine. The plan is to take this conversion on one axis at a time. And since Z is what goes on first, that's where I'm starting. If all goes well, by the end of this video, we'll have this thing going up and down like Sir Mix-a-Lot's hoopty. My apologies, I am so embarrassed. It's since come to my attention that Mr. Mix-a-Lot's hoopty might not have actually gone up and down. I'm glad I managed to save that. All of the initial cuts were coming out a bit ragged. In fact, that last bore, or the first one rather, still isn't as smooth as it could have been. And then I realized I was trying to hit metric dimensions with an imperial boring bar. I switched to a metric boring bar and smooth as silk. In theory, this shouldn't be too difficult, at least not the way I've opted to do it. This is the side of the Z-axis, that's the machine column, and this is where the X-axis screw installs. Probably what we'll do next video. Here is where the hand wheel used to go. Turning this would manually lift and lower the table. Instead of installing this hand wheel, however, we'll install a motor. Not exactly like this, but it's basically what we're doing. Instead of turning the crank, we'll let our fingers do the walking. I mean, let the motor do the turning. Let this do all the hard work. I need to now pick up the center of those features that I just machined. That will become my origin. I've just sort of eyeballed the part in the vise. Would you believe me if I told you I centered this part by eye to within 1/10,000? Eagle-eared viewers, or those of you with not much else going on, may have noticed I've left the original lead screw in the Z-axis. That's to say there's no ball screw here, where you'd reasonably expect one in a CNC conversion. We'll get into ball screws in the next video because the other axes have them. And I'll be honest, I'm not 100% about leaving this in here. I don't really like how it feels when I turn it by hand. Though I don't have all the bearings installed yet, so I'm hoping that's a big part of it. Not to mention the fact that CNC will likely wreak absolute havoc on this poor screw. But I have it, it's in great shape, and a ball screw Z-axis brings a lot of headache with it. But instead of trying to justify my decisions to you, who, consequently, are not the boss of me, I think I'm just going to try it. I mean, it's there, and it's easy-ish to do. But the odds are pretty good by the end of this video, once we have this motor on and everything is moving, I'll change my mind and gut this again. If it does work well, maybe we'll leave it in and torture test it. See how long a screw like this lasts in a CNC conversion. I've since gutted all of the insides out of this machine, all of that clockwork that ran this all in one motor. There are no more gears down here. There's nothing left in the apron. And I don't think it's really that hard later to lift this up slightly and retrofit a ball screw. You may be wondering why that spline shaft is back there. I did just say after all that I eliminated all the extraneous junk. Fact is, I couldn't figure out how to get that dang thing apart. It was not coming out of that subassembly we saw a video or two ago. It might be a press fit, and I was about to push it out when it dawned on me it might be holding in some of the other components. So I just left it. It doesn't do anything. It's just dead weight for now, going along with the ride. Since it's painfully apparent no one else is going to say anything, allow me to broach the subject of servo motors. Let me put on some coffee and I'll meet you back at the... This is a stepper motor and this is a servo. Yeah, despite me going to a lot of trouble to show you these, I'm not going to get into the specifics. First, I don't want to bore your faces right off. If you're really into this stuff, snoop around, you'll have more than enough to read. Second, we'll be getting into some of the details later on the servo when the machine is together and we're fine-tuning it. And third, frankly, I don't know that much about them. In fact, this is my first run-in with servos above and beyond those little hobby things you might drive with an Arduino. But you know what caught my eye when I first unpacked these? I mean, check out that body size. The stepper's almost twice as big. But have a look at the difference in the size of the spinny end. You don't just throw in a keyed shaft of that size for nothing. This servo is packing some heat. But let me tell you how I got here. The one thing I knew going into this is that I wanted to do something closed loop, meaning I wanted the motors and the control system to always know where it was in time and space. One of the frustrations with the steppers in my CNC router, if I get too aggressive, like if I push the machine too hard, the steppers in this router will lose their place and screw up my parts. Like the computer will tell the motors to move to some location, but along the way they stop to buy some magic beans or something, I don't know. And the computer doesn't know that. The controller loses track. On the next move, the controller will move the tool based on where it thinks it is, not where it might actually be. And that's a problem. A problem I want to avoid with my mill conversion. This system is open loop, and I knew I wanted closed loop for the mill. But other than knowing those words, I didn't know how to get there. I also knew I would need a ton of torque. Maybe not 2,000 pounds, but a ton nonetheless. And I wanted to be able to maintain that high torque through a decent range of speeds. Steppers typically start off with pretty high torque at low RPM, but that drops off as they speed up. I didn't want the motors losing their will to live if it turned out I could drive the mill at lightning speeds, which I don't expect I'll be able to, but we'll get to that later. So I sort of knew where I wanted to go, I just wasn't sure how to get there. But if there was one thing I learned in grade school, it was this. There are two types of knowledge. There's knowing something yourself, and then there's knowing a guy who might know a guy. Know what I'm saying? So I sent an email to Mr. Brian Barker of Newfangled Solutions. They're the ones who brought us Mach 4, the PC control software I use on my router, and the one I'll be using on my mill. Who better to ask, right? I said, Bri, here's what I'm trying to do, dude. He cut me off mid-sentence. This is in an email, mind you. Told me never to call him Bri ever again, and just go with EtherCAT servos. I was like, what kind of a cat? So I got to doing my homework, and the more I read about EtherCAT, the less I understood. Let me rein this in, otherwise we'll be here forever. As I was trying to learn the ins and outs of this alien technology, would you believe what happened? A box showed up in the mail from Brian. He sent me motors and an EtherCAT control system. Can you believe that? That's the nicest thing anyone... I know what you're thinking. Hey, old Tony, are you trying to sneak in a paid promotion? I most certainly am not. In fact, Newfangled doesn't even sell this stuff. You couldn't buy it from them if you wanted to. Turns out, Brian's just a really nice guy who likes what we're doing here. Alright, since we're getting all sappy here, I'd be remiss if I didn't give a shout out to my patrons. Your support really does go a long way. I know you knew it'd be a thankless job, and I said there'd be no special treatment. And although I love each and every one of you goofy viewers, I love you patrons just a little bit more. Alright, we're close. Almost ready to put this thing together. There is just one more piece I need to figure out. This is the bit from the mill that the Z-axis hand wheel was attached to. If I can remember how this went together. This had a shot bearing. I have a brand new replacement. We'll install this later. But this looked like... Am I doing this right? Alright, I'm not doing this right. But that's where the hand wheel went. If you wanted to raise and lower the table, you'd turn this hand wheel. It would turn that shaft, which was connected to that sub-assembly gearbox that turned the screw. I'm simply removing the hand wheel and attaching a 2-to-1 timing belt system, pulleys and belt, using this bracket we made to hang the motor on there. Motor fits through there. This whole thing installs right back where it came off, and when we're done we'll build some sort of a shield or something so fingers don't get cut off. Before I can do this though, I've got to figure out what's up with this little jack shaft thing. This is the line that fed hydraulics to the brake, that sort of collet closer looking thing we saw in the other videos. This thing was tough to turn right off the truck. I don't know what's going on in here. I expected to find a gummed up hydraulic lock in there, but best I can tell, it's doing okay. It's got this weird split nylon or something plastic ring in there with a screw that comes from the outside. Maybe that's swollen up a bit. I don't need any of that stuff. But the little jack shaft has got these weird features on it. It's got this spiral groove. Have no idea what that does. Maybe to get oil to go somewhere. This thing that looks like a shoulder machined into the shaft is actually a Sprag clutch, like a Sprag bearing. It'll rotate one way, and quite smoothly at that, but not rotate the other way. Like I can drive the shaft with this. This appears to coincide with that plastic locking collar. So I suppose it was free to turn in one direction, presumably to lift the machine, and then maybe you can dial in the drag for the other direction? I don't know. I've never seen anything like that. Not even sure why you'd want something like that in there. And that, my friends, is why I'm not a milling machine designer. But what I do know is I no longer need any of that junk. So I'm going to break this down, clean it up, take out any of that stuff I don't need, install a new bearing, and when I'm done, I guess I'll see you over at the machine. This little handle extension cleaned up pretty well. There was a bunch of gunk and old oil on the inside. I removed that Sprag clutch and just made a replacement bushing / bearing out of bronze. All in all, it feels pretty good. I've got a servo on the mounting flange, just in there loosely. This flange is held on with set screws and a couple of pins. I'm just going to use the set screws for now, wait to pin it later. Part of me is worried I might run into the x-axis, so I may have to turn this a bit. Run it through its paces, just make sure I'm not interfering with anything. I'm going with a belt reduction because these motors are capable of speeds that I think exceed the capabilities of this mill. Like with these ball screws, these motors could technically push everything like somewhere around 300 inches a minute. I don't know if the weights involved and the dovetail waves on this machine could handle that. But if I got this to around 100, I'd be over the moon. It would have been great to do a 3-to-1, but then the timing pulleys just get silly. Alright, design failure number 1. I didn't give myself access to tighten the set screws on the larger timing pulley. The hub of this pulley nests into the bracket, and now I can't get at those set screws. I'll have to mill a slot or two. For belt tensioning, I've added a little jack screw that can push up against the flange of the servo. It's not much, it's only about 60 thou, a millimeter and a half. But it looks like that should be enough to get me close. Before we power this up, let's take a moment and talk about the hardware. Again, we've got two things going on here at the same time. EtherCAT control and servo motors. You can do servo without EtherCAT, of course, And I suppose there's probably other stuff you can do with EtherCAT that doesn't require servos. I know enough now about EtherCAT to tell you with confidence that I know nothing about EtherCAT. Check this out. The drives are just daisy-chained together with Ethernet cable. One cable just goes to the computer, and then you just jump from one drive to the next. Out of one into the other. Out of that into the next, etc. You want to add 15 more axes to your machine? Just string in 15 more drives. I mean, it's like plugging in Christmas lights one after the other. Fire hazard? Maybe. Easy and convenient? You betcha. Heck, I bet if you plug a network printer in one of these drives, I bet it'd work. Doing some interneting, a kit like this one, motors, drives, and control, I mean, not pulleys and belts and hardware like that, depending on which one you get, as of today, is somewhere around 2,000 clams. Now, off the cuff, that probably sounds like a lot of money, because it is a lot of money. But for what you get, at least what I'm seeing so far, it's really not that much more expensive than what I spent on my router. I mean, just look at this stuff. Breakout boards, transformers, power supplies, heat sinks, relays, I/O boards, fans, buttons, switches, and none of this is really necessary anymore with that EtherCAT system. I literally took them out of their boxes, plugged the drives straight into the wall, and connected the motors. I mean, I haven't done the math. You might save a couple of $100 doing it this way, but this control box alone is weeks worth of work. Then we've got the servos. The number one thing I love about these, compared to the stepper setup we just saw, and this might sound stupid, especially considering some of the other features we're about to see, is their complete immunity to noise. I banged my head against the wall for days, routing and rerouting wires on the other CNC, adding shielding, figuring out they'll get glitches that can stop the whole thing in its tracks. Well, not so much these days since I sorted the grounding, but this servo system, absolutely none of that. Second, but certainly not least, these of course are closed loop. Meaning they have encoder feedback and they always know where they are. No more lost steps. These aren't currently energized, but if I turn these, you should see that they're keeping track of their position. These particular servos also stay on the clock even when they're completely powered down. If you unplug the machine, there's a power outage, they still know their place in the world. Somewhere in this power cord there's a battery of some kind. But you know what that means? I no longer have to beat my kids when they wander into the garage and start moving the machine hand wheels while I have a critical setup on the machine table. These servos just might save my marriage. I no longer need limit switches on the machine itself. No more homing. Again, the computer, because of the closed loop servos, always knows where stuff is. And silly as this might sound, that closed loop feedback also lets me use the servos as a DRO system. If I want to manually machine something, sometimes you just need to drill a hole or mill a simple slot. I don't need to go to all the trouble of writing any G-code. I could just use this as a manual mill with DRO feedback. I'm not saying this is a Shaolin killer just yet, because it can hear us, but maybe. Enough talking, let's power this up and see if it works. This thing is a lot louder than I was expecting. Though to be honest, it's just as loud as it was when it was running the pancake motor, so I'm not sure why I'm surprised. I thought it was the bevel gears in here that turned this input shaft 90 degrees down to the screw, but a good portion of it seems to actually be coming from in here. I'm going to open this up again, or maybe I'll just scrap this whole thing and make my own extension. Next video will be the X-axis conversion. Proper conversion with a ball screw. Heck, maybe X and Y if I'm feeling particularly overachievy. But the Z-axis saga isn't over yet. This servo, well, all servos, will need to be tuned to run correctly. And they should be tuned under load. Meaning, to do this right, I need to get all the rest of the parts back on the machine. Which contrivedly brings us back to this screw. Well, maybe not this screw, but the lack of a ball screw. What I've done here, just swap out the hand wheel for a motor, is the 20% work that gets me 80% there. Now, between me and you, I'm still torn up inside about what to do. My opinion has changed 15 times in the course of just making this video, but as of this very minute anyway, I think I'm just going to leave it in there. See how much of a problem it really is in actual use. Almost definitely the bottleneck. But other than the general feeling of it cramping my style, I won't know how big of a hit this is until I've tuned this in and make some parts. I really don't know how you and me ended up milking a simple hand wheel conversion for 23 minutes, but here we are. I'm super excited about this project finally starting to come together and can't wait to start making some chips. I'm not sure if the next video will be mill conversion, but for now, I hope you enjoyed that, and thanks for wait a minute. I've got some news. This stub shaft connector thing for the hand wheel was really bugging me. I think I mentioned earlier it was noisy and I couldn't figure out why. Long story short, I broke it down, installed a bearing in this small end. There was enough meat in here to sort of counterbore a seat for the bearing, pushed in the bearing, added a little clip, and it is a ton quieter. I mean, it's still making a lot of noise, but it seemed like most of it now was coming from the belt. So what I did was pulled out the thermal camera, and would you look at that? I mean, that's not a good read on the aluminum, but it was very apparent at the machine, the stub arbor or whatever, this thing, wasn't warm, but I started to feel the top of this aluminum hanger plate warming up, and that belt was pretty hot. I don't know if I've ever run into anything like that. I'm not quite sure what to do. Maybe move to liquid-cooled belts? I'm not sure. Adding that bearing, though, got me quite a bit of speed back out of the machine. I mean, the motor still isn't tuned. Up until now, I could push it at about 60 inches per minute, 55, 60, before the system would trip out. I'd get some kind of encoder error, something. With the addition of that bearing, I'm now at 80 inches per minute, and the acceleration setting, at least according to in Mach 4, is 0.75 G, which is a big improvement from what it was doing before. If you go back and watch when it did the transitions between up and down, it would sort of decelerate slowly, stop, and accelerate again. Now it's pretty snappy. I don't know if I want to push my luck. This machine, brand new with the pancake motor, I think the spec sheet said 40 inches per minute. That's going to be a bottleneck for a CNC. And if I drive it at 80, I mean, I don't know if I'll just melt this whole machine, but we'll burn that bridge when we cross it. I appreciate everyone who stuck around and kept me company. It's a lot more fun than hanging out by myself out here. Thanks for watching.